So it's a personal pleasure for me to introduce our next speaker, Marco Cusumano-Towner, who's a PhD student in my lab and has been working for a couple of years now on Gen, which he'll be talking to you about.
Hi, yes. So I'll be presenting some joint work with Vikash on Gen, a probabilistic programming platform for probabilistic AI. So I'll start off by motivating the work by showing some examples of the types of applications we'd like to support with this system. In particular, some applications from visual scene understanding. And then I'll introduce the modeling and inference syntax of Gen using a simple statistics model, a simple Bayesian robust regression model, where for inference we're going to combine MCMC and map optimization. Then I'll introduce some of the core technical ideas in Gen, in particular the notion of a Gen module. And then I'll provide a second example where we use a combination of deep learning and inference networks, the deep learning and importance sampling for 3D body pose inference from depth images. So here's a recent paper. This was just published on arXiv last month, or 2 months ago. And this paper shows how to estimate the 3D layout of an indoor scene from a single RGB image. And this paper does this using a generative model of the layout of these different CAD models of objects in the room, as well as a model of the process of rendering to get the image from these 3D objects. So in principle, we would think that since it's a generative model, we should be able to apply some of our probabilistic programming tools to do inference. But in this paper, there's a section on inference, which is a few pages long. It actually takes a while to describe, because it's this heterogeneous inference architecture that has several stages. So for example, there's 2 different convolutional neural networks, one that sort of initializes the room geometry, another one that initializes, along with some heuristics, the 3D location of each object and its identity in the room. And after you run those initializations, the authors run a simulated annealing MCMC algorithm to iteratively adjust and improve the layout of the room. So if we want a system that supports very kind of customized heterogeneous inference strategies like that, we need something that basically provides a lower level of programmability. So that's what we've been focusing on in Gen. And there's some previous work which is closely related. This is the picture system from 2015, where they addressed a similar problem, and they actually used probabilistic programs to express the prior distributions on these 3D objects or these scenes. And they also used a heterogeneous inference architecture involving a combination of different types of bottom-up proposals and gradient-based MCMC. So in order to support these sorts of applications, we have a few different design goals when we're developing Gen. So in particular, like I said, we want to basically support multi-paradigm inference. So for example, we want to support sort of Monte Carlo inference in structured generative models, including general sort of Julia or general probabilistic code. And we also want to support sort of deep inference networks like were mentioned earlier today, as well as numerical optimization. And the second key design goal is that we want highly programmable inference. So instead of presenting an interface to the user that says solve this inference problem using this algorithm, we want basically users to program the algorithm themselves, but using a higher level of abstraction than they would if they had to do it from scratch. And so the types of inference strategies that we want to be able to express include things like use Gibbs sampling on these random variables given these other ones, and alternate that with some map optimization. Or more advanced techniques like custom reversible jump moves. So can we make a system that provides some support for that? As well as things like custom SMC and MCMC proposals and auxiliary variable samplers. And also I think it's important that if the user can't implement the algorithm they want in the system, they shouldn't necessarily have to give up on using the system. They should be able to maybe use pieces of the system that they can, and then write their own code out externally. And then finally, we want to address some performance problems that have popped up in the past due to these other 2 requirements. So basically, it would be ideal if we could get out-of-box performance that was in some cases competitive with hand-coded samplers. But even if it's not, we would like to provide an incremental optimization path for users to take the slow parts of their algorithm and sort of do more hand coding, maybe for a bottleneck part of the inference algorithm. Right, so we could just program from scratch in one of these existing languages, right? We have full flexibility and there's no performance or constraints on the inference algorithm, but we would like some intermediate levels of abstraction to make this easier. So that was sort of the overall motivation and sort of the goals of Gen. Now I'll just introduce some modeling and inference code. So this is a simple toy problem where on the left we have some x and y coordinates, and on the right we've filled in some annotations with latent variables. So we've said, okay, there's probably a line, there's probably two different noise levels that explain this line, some for the outliers, some for the inliers, and we know probably which data point applies to which of these noise levels. So here's a generative model in Gen from which those inferences were derived. The top level of the model is this Gen function called model, which a Gen function basically extends a Julia function with probabilistic semantics. And this Gen function takes as input a vector of x coordinates, samples a few random variables. Those are the latent variables explaining the line and the two noise levels, one for the inliers, one for the outliers. And it gives an address using this adder expression to each random variable. And then it samples the y coordinates, and it samples that by running this other Gen function called datum and applying that to each x coordinate. And for each x coordinate, it makes a Bernoulli random choice where it decides whether this is going to be an inlier or an outlier, and then it draws the y coordinate from the normal distribution. So there's this hierarchical space of random variables. So at the top level, we have slope, intercept, and the two log noise variables. And those appear at top level in this assignment. All the y variables are located, in this at a hierarchical addresses. So for example, the second y coordinate has address data, then 2, and then y. So basically, each function call introduces a sort of local namespace for random variables. So this is really, I think, the most important slide, which is showing how you program inference in Gen. And basically, this is just a Julia function. So this is getting at the point that inference code is just regular code. But this Julia function is going to use higher levels of abstraction that are built into the system. So this function takes as input the data set, and it begins by constructing an assignment, which is going to be a partial assignment to this probabilistic program's trace. That's going to include just the y coordinates. So the syntax here with data and then right arrow I, right arrow y, basically means indexing the address of each particular y address. So given this partial assignment, which we're going to call observations, we pass that into this generate method, which is part of Gen's module API. And this generate method takes a given Gen function and observations and arguments and returns a complete trace of the function. So now we've basically filled in the random variables with some values. And they're not compatible with the data yet because we haven't done any inference, really. So the rest of this code is just a Julia for loop that's doing an MCMC Markov chain. And inside each loop, there's sort of two blocks. One is doing some gradient ascent moves or map optimization moves on just the parameters. And then the other is doing this custom Metropolis hasting move, which is proposing to switch the outlier indicator variables. So the map optimization and the Metropolis hastings are two parts of Gen's standard inference library. And the standard inference library basically takes traces as data and returns traces as output. Right, and at the end of inference, we have a trace that's compatible with the data. And in Gen, like in some other systems, custom proposals can be expressed also as probabilistic programs, in this case, Gen functions. So here we have a custom proposal that just deterministically decides to flip this outlier indicator variable, this z variable, and then it will accept or reject using the MH rule. So that sort of programmable style of inference is building on ideas introduced in this venture system, which was the predecessor. But one of the issues that we encountered with venture in the lab it had to do with performance, basically. So we've been thinking about performance, and with Gen's system, I'll talk more about how we get performance later, but basically we've iterated over a few different variants of the system, and actually each of those variants has been more performant than venture by at least an order of magnitude. in terms of milliseconds per sample on the x-axis and accuracy on the y-axis. And in another variant of this model, which is collapsed, we compared against hand-coded samplers and STAN, and the static variant of Gen basically got the same performance. So these are preliminary benchmark results, but at least they show that we're able to sort of push performance with additional effort higher and higher. So the current version we've settled on is this Gen-JIT version, which has a balance between performance and system complexity that we think is appropriate to start with. So now talking a little about Gen's internals. So one of the problems that I mentioned, or one of our goals, was how do we integrate multiple inference and modeling paradigms. So examples of these different types of paradigms are in Monte Carlo, we might want to work with arbitrary generative code in Julia. And that might involve, doing that efficiently might involve fast editing of execution traces of MCMC. And maybe if we want to do custom SMC, we need to have some way of doing fast resampling of execution traces. And for deep learning, we might have these models, which are basically these large differentiable array computations, but we want to somehow mix that with Julia code. So for deep learning, we're integrating with TensorFlow. And the computation is characterized by these batched gradients with respect to these large parameter arrays on a GPU. And then another example of a different type of computation involved is gradient-based inference with respect to maybe tens of random variables scattered throughout the trace. So this might be appropriate for a scene understanding application where you have a few random variables describing the object pose. So that was one of the challenges, and basically our approach is to create the system in a very modular way. So we have these Gen modules that each implement this Gen module API, which basically exposes a bunch of procedures for creating, updating, and transforming execution traces. And that generate method was one of these module API methods. But the point of this module API is that we can have very different implementations of the runtime system that are specialized for different types of computation. And this module API can be subject to custom JIT compilation passes, which let us exploit specific features of certain types of computation. And I'll show a picture of that in a moment. But on top of the Gen module API, there's this higher level set of abstractions called the Inference Standard Library. So Metropolis Hastings and Map Optimizer are two examples from there. There's also a method for training using this sleep algorithm or amortized inference. So there's sort of an open-ended set of abstractions there, and those are all written in user Julia code, so it's very extensible. So just to give an example of sort of how this heterogeneous architecture looks like. So basically, these are all different types of Gen modules, and each one implements sort of a different runtime. So one type of Gen module is basically implements a very lightweight random database style of probabilistic programming. And another type of Gen module basically is expressed using a very restricted DSL, which expects static single assignment blocks, and it's able to compile those to basically Bayesian networks and generate more efficient code that way. And then TensorFlow modules are another distinct type. And then there's also higher order modules that express sort of different types of structured repeated computations, like plates, which is analogous to this plate Bayesian network notation, as well as Markov models and so on. And users can also define their own modules because we have this extensible layer where we have an API. And finally, this is a compositional API so that these module types can invoke each other. Okay, so that was some of the technical ideas in Gen. So now just to wrap up with one other example, closer to the AI applications we're interested in. So here's a structured representation of the pose of a human body, parameterized by a few joint locations and a global rotation. So given that we have a 3D model of the body, here is a mesh rendering. And then from the mesh, we can apply some rendering software to generate a depth image in this case. And it's actually a blurry and noisy depth image. And then the task of inverse graphics is basically of recovering the structured representation from this noisy image. So here's some Gen code representing the generative model. So there's some Gen function that just encapsulates the prior. And then the prior, body pose prior function returns this pose, which is just this struct. And then we pass the struct into the renderer, which internally is doing this work. Then we run some Gaussian blur code to sort of smooth the likelihood function a little bit. And then finally, we add some pixel-wise noise. And again, this is sort of the address schema of all the random variables made in this generative model. So during inference, we're going to constrain or observe that particular random variable, and we're going to try to infer the other ones. So in this example, we're going to use an amortized inference approach. So this is the generative model in graphical model notation on the left, and here's our importance distribution in graphical model notation on the right. And basically, there's going to be a convolutional neural net, which we're going to implement in TensorFlow in a TensorFlow module that's going to parameterize a bunch of beta distributions on the parameters of the pose. And we're going to train using this sleep phase or amortized inference objective. And yeah, so here are just this is a sort of a tutorial set of results explaining the types of inference that you can get and the sorts of different differences in performance. So if we just run samples from the prior, you can see those on the left. Importance sampling with a prior proposal is very inefficient, as we'd expect. If we train the deep neural proposal and just sample directly from it, it takes, let's say, 8 hours to train a deep GPU in this case. And it basically is very confident about the pose, except for it can't really get the right uncertainty over this particular parameter, the elbow. So just by running a relatively small number of importance samples, we can correct for that. So here's some gen code showing the syntax of how you construct that. So on the top is a gen function again, expressing the proposal distribution, for this time for importance sampling and not for MCMC. And part of that code basically invokes this neural network, which is implemented as a TensorFlow module. So this is a little DSL that we wrote, just very lightweight, that just lets you express functional TensorFlow blocks. And this integrates with Gen's automatic differentiation through this module API, which sort of allows for compositional automatic differentiation. So after it runs the neural network, it then takes the output layer and runs this little prediction gen function, which just samples from these beta distributions to predict the pros parameters. And for training, we might want to batch the neural network or run it in a vectorized fashion. So we can just write a batched variant of the proposal that takes in a batch of images and then runs the predictor on each one in sequence after running the neural network. Right, so I'll just briefly show sort of the type of code you write. So for training, there's a little function train batched, which is part of the Gen module API, which takes in the generative model and a proposal, a batched proposal in this case, and does the stochastic gradient optimization of the TensorFlow parameters. And the update is actually, the parameters never leave TensorFlow, right? They're always sort of they're sort of local to the module, local to the TensorFlow module. And then it's pretty easy to do sampling importance resampling after you've trained this neural network by constructing these observation assignment again and passing that to this importance resampling method in the standard library and then getting the trace out and reading from it. And again, this is showing sort of one of the system ideas in Gen, which is this compositional automatic differentiation enabled by this module API abstraction. So here we have a dynamic Gen function, which was what the proposal itself was. And that guy invoked a TensorFlow module. And sort of this is showing how the reverse mode AD in dynamic Gen functions is interacting with TensorFlow's gradients operator. Okay, so I introduced Gen, which is a probabilistic programming system. It's still a prototype. There's not even a README on the GitHub repository, but that will change soon. And we aimed for a multi-paradigm and programmable system that had good performance. One of the key ideas was this Gen module idea. And basically, sort of the implementation level, we sort of just chose to embed this in Julia, and we included TensorFlow integration. So that's it. Thanks.
I was curious about a particular point that I think is a broader question about the abstraction. So when you're doing the model where you do some gradient descent to optimize some parameters and then have some MH, I would imagine that for the MH to work well, what you really want to do is make a proposal, optimize its parameters, and then accept reject, because otherwise you have a starting point with optimized parameters and a proposal that might not be appropriate to those. Is there a way to achieve that kind of interaction between the pieces?
Yeah, so one way could be implementing a proposal, joint proposal, that maybe actually does some sort of auxiliary variable annealing or something over some of these continuous variables. So that sort of auxiliary variable approach you can implement in the system, basically.
As a new method, or using those methods?
So actually mostly using the existing abstractions. Basically you would implement let's say, an annealed importance sampler algorithm, and then you would invoke that algorithm from a proposal function. And it would basically, yeah, if that makes sense. Any other questions? Hi, yes.
This may not be a pure end question, but are there any libraries you're aware of that could use data to make some sort of recommendations for starting point? I mean, is there any interplay between some of the stuff that Julie will do presenting with Metaprop and Gen? Maybe a totally ignorant question, but are there any connection points there or libraries that could help using data first and then sort of suggestions to sort of do the proposal? Is the question clear?
I'm not exactly sure I understand the question.
Are you familiar with Metaprop?
Yeah.
So is there any work that's been done using Gen like Metaprop?
Oh, so, yeah, not yet, basically. But there's some similar choices in the design and architecture, and yeah, we hope to do that soon.